Good morning, all. Welcome. Today, we will have a presentation at the department seminar series by Professor Talea Mayo. The title is Computational Modeling of Coastal Flood Risk under Non-Stationary Hurricane Conditions. Dr. Mayo is a computational scientist that develops cutting-edge models to understand how evolving coastal flood risk will impact communities. Her research surrounds the physical processes of hurricanes, storm surges, sea level rise, and morphodynamics, but she also investigates societal impacts to better understand vulnerability in an effort to improve resilience and adaptation efforts. In the classroom, she teaches foundations of computational mathematics, and outside of the classroom, she spends time nurturing her human and animal dependence between powerlifting, distance running, and immersing herself in the arts with family and friends. Thank you very much, Dr. Mia, for doing this, and it's all yours.
Okay, so let me try to share just like I did before. Um, okay, are we good? Good. Okay, so thanks for having me. It's a pleasure to be here. This is the first talk I've given in a bit because I was doing a mathematics lecture series and wasn't doing additional travel. So it'll be nice to engage with some scientists and engineers. So I met Professor Rode Barbarigos in Princeton in civil engineering. So I'm in the Department of Math now. But my, I guess, professional training has been in civil engineering department. So I was at Princeton, um, I guess 2013 through 15, and then I was at the University of Central Florida in civil engineering from 2015 to 2020. So very interested in civil engineering applications, and hope we can build some collaboration. So today I wanted to discuss kind of the main research interests I have, which is understanding coastal flood risk under non-stationary hurricane conditions, and I'll explain a bit what that means. So though you are no stranger, unfortunately, to hurricanes and their hazards, I'll start by introducing the problem that I study and then how we model it using computational mathematics. And then my main applications, which are risk analysis, and I've done that deterministically and also probabilistically. So, coastal regions are of interest to me because they're the intersection of both physical processes or like geophysics and science, and then also the built environment or civil engineering and where the nature is interacting with humans. Additionally, coastal regions, which are defined as like 100 kilometers from the coastline, I think, are home to more than 40% of the US population. And this is only increasing. So in 2015, it was projected that the coastal population would increase by 50% by 2060. So unfortunately, coastal regions are also at an increasing risk of natural hazards. And so particularly when I sat in civil engineering departments, I studied two main natural hazards, which are flood and coastal erosion. So I haven't focused on erosion as much lately, but hope to get back to that. Um, and so I've primarily been focused on coastal flooding. So my interest in coastal flooding developed when I was living in northern Louisiana and Hurricane Katrina struck the Gulf Coast. And so, if you're unfamiliar because you're younger than I am, then Hurricane Katrina, the big catastrophe there was a levee failure, which caused the city to flood. And then there was also civil engineering infrastructure failures that kind of prevented quick pumping out of the water. And then that just had a number of cascading impacts. So, this was really devastating to the people there. And that's when I got really interested in hurricanes themselves, and more atmospheric research in this particular application of math. So what I learned as I studied more was that the problems from Hurricane Katrina were not directly from the hurricane itself, but rather the storm surge and the flooding that it produced. And so I will just start by discussing that hurricane storm surge is defined by NOAA as the abnormal rise of water generated by a storm. So we have a mean sea level, right, which is subject to normal variations due to the tide. So you have like a normal high tide, but then you have additional water on top of that produced by a or a hurricane blowing ocean water onto land. And so I think a simplistic way to think of this is that you have bottom friction of whatever may be on the ocean floor or the topography, meaning like buildings or houses or concrete. So the friction there is resisting fluid flow, and then the wind is pushing fluid in the other direction. So it's kind of this fight. And so if the hurricane is strong enough or all of the factors align enough, then you have a net result of coastal flooding. So I, in my research, in my dissertation research, and since then have looked at kind of these two components. What do bottom friction and then also hurricanes themselves mean for coastal flooding? And then what are the best way to model these computationally? How do we use data to improve our estimates of these things? How do we characterize the uncertainty? On and on. So my mathematics problems all kind of center around understanding this hazard. So coastal flooding is what I like, kind of the general term for all of the water that would come from a flood or from the ocean itself. And so storm surges pose the greatest threat to life and property from a hurricane. So as I mentioned before Hurricane Katrina, or before I did kind of the research around it, I think of a hurricane and I think of probably the same things you do. Like what category is it going to be? How bad is it going to be? And that's kind of our association, right? If it's a category 5, then we're evacuating and we're expecting a lot of damage. And otherwise, we're kind of not. But what's true is that the category is describing wind speed or how fast the hurricane is rotating, and that's not the same as how much surge you can expect. And it's the surge that actually produces the most deaths historically, largely because of Hurricane Katrina, which caused 27.8 feet at its peaks in the Gulf. So more recently, or let's say like since Hurricane Katrina, there was a greater emphasis on emphasizing the storm surge in emergency management. So National Hurricane Center came up with more products to, instead of just saying it's a category 1, it's a category 2, also illustrating what was the risk of storm surge in some ways. So these days, when there's a hurricane approaching, then we'll see things messaging like the one on the right, where usually the first bullet that they say pertains to the storm surge. So expect life-threatening storm surge in blah, blah region. And then also these products have been developed so we can kind of see who needs to kind of be watching out for storm surge. And so I wrote a paper in 2021 with one of my graduate students, kind of observing historically this phenomenon of focusing on hurricane intensity, or the Saffir-Simpson wind scale, and the categories, and how it doesn't quite relate to the actual threat. So there's a lot of background on why storm surge is so important and so interesting to me. So if we think about storm surge risk, risk can be defined as a product of hazard, exposure, and vulnerability. So if any of these things increases, then we have increased risk. If you have more storm surge, you have more risk. If you have more exposure, or let's say property exposed to the storm, then you have more risk. And if you have more vulnerabilities, which can mean different things like your ability to evacuate, or transportation, or physical ableness to leave, then you would have increased or decreased risk respectively. And so when we talk about storm surge, we're really talking about the hazard or the science that's increasing risk, right? So there's a storm surge doing? There's kind of not anything we can do about it. If it's coming, it's coming. But civil engineering has more to do with the risk comprehensively, right? So structures can be built, for example, to mitigate risk by like lowering exposure. So if we build in a seawall or we build in a levee or we have social infrastructure so that people are protected, these are matters of civil engineering. And so that's why I'm so interested in continuing to work on civil engineering problems and collaborating with civil engineers. So usually some of the measures that can be taken to reduce risk have to do with the exposure and vulnerability. And so these can include natural measures, nature-based measures, structural measures, and then non-structural measures. And if we were in person, then I would stop here and ask you, what do you think are examples of these? So I'm going to do that in a second after I discuss the first three. So I'm going to ask you in like 30 seconds, what are examples of non-structural measures of civil engineering interventions, let's say. So natural measures for reducing storm surge risk might be like a protection of a wetland. So it's just kind of things that are already there. So wetlands or mangroves or something like that is just naturally existing already. And so it increases the friction over which the fluids would flow. And so kind of naturally reduces storm surge. Then we also have nature-based measures, which are things that are kind of based on nature, but not naturally there. So you could think of that as like green infrastructure. So planting vegetation to achieve the same effect. And then usually when we're thinking about civil engineering infrastructure, we think of structural measures or gray infrastructures like building a seawall. But then also we have other things that I would call civil engineering measures, which would include non-structural approaches. So does anyone want to unmute and or chat and suggest or like think about what might be a non-structural approach to reducing storm surge risk?
Codes, changing land use, planning, then, moving
Exactly.
properties, relocation, things like that. And then I'll shut up and let
Exactly.
the students say whatever.
Yeah. Anything else? That was pretty good. I should have said no experts, but yeah, so I think those are the kind of interventions, right? So the first thing you said was land use, right? So if you decide to build a new mall on the coastline, that is reducing first of all, you're probably getting rid of some of the natural measures that are already there, but you're also basically reducing the friction that would naturally kind of buffer the storm surges. So that would be, I guess, an example of a failure of civil engineering measures or engineering measures. But also like relocation, insurance prices, right? These are kind of non-structural things. They're not physical things, but they're things that would reduce your risk of storm surge because they might reduce your exposure. So if you move or you implement policy about where you can build, then that would reduce exposure and thus reduce risk. So there's kind of a lot of interdisciplinary problems that I'm really interested in understanding kind of what are the impacts of storm surge risk and then how can we reduce it. Okay, so I won't talk about that too much today, but kind of the point that I want to make here is that your true coastal resilience or truly reducing coastal storm surge risk requires some sort of long-term planning and risk analysis, right? It's not usually a thing that you can do just because a storm is there, right? All of a sudden, we're going to be resilient. We have to kind of plan ahead. So a lot of my work is about that. And so on top of having kind of all of these risks currently, then what we understand is that our risk is actually increasing. So I talked a couple slides ago about how This is relative to kind of your normal variation in your tides around the mean sea level. And so we understand, I think you guys know well, that your sea level is rising. So even the tides are coming in further than they would have. You have sunny day floods. Um, so the risk is basically increasing because of that. The hazard is increasing. So you have sea level rise, and that's pretty well studied and has been, or I mean, it's kind of intuitive that if our mean state is increasing, then when a surge additionally happens on top of that, that would increase as well. But my postdoctoral work was really understanding the effects of how the storms themselves in are causing increased flood risk. So not only is sea level rising, but hurricanes are also changing the structure and kind of the intensity or the expected frequency, et cetera, is also changing as the climate changes. And so that is producing increased risk too. And so what you're seeing here basically kind of qualitatively is that we're progressing in time, and then we're seeing more and more blue, which is indicative of like a flood plain. So the 100-year flood is here. I think it's 100, 500, and 2,500 or something like that. So the point is that as we go ahead in time, then we're seeing areas at risk that maybe weren't at risk before, and then also kind of a higher level of risk for the areas currently at risk. And this is described in terms of like a 100-year flood, as I said. So I'll say a bit more about that later. Yeah, kind of the point is that we not only want to think about sea level rise, but that the hurricanes themselves have an impact too. And so that's pretty much what I am most interested in. How is coastal flood risk changing due to these expected changes in hurricane climatology, we call it. So for this, we want to use coastal, let's say, computational models, right? So we can't rely on data because the climates that we're curious about presumably haven't occurred yet. So physics-based modeling comes in handy here. So we can put in different scenarios and understand kind of what would happen if, something were to change. And so the models that I use are all based on some simplification of Navier-Stokes, where we're depth integrating in the vertical direction. So we're not assuming like gradients in the vertical direction. Everything is depth averaged. And then we have conservation of mass and then conservation of momentum, and then everything's coupled. But we solve these models for H, which is like a total water level. So here in the brown, you have like the bottom of the ocean floor, and then here you have the top of the water column. And so if we know the length of H, then we know how much water we can expect in a particular place. So this is the main thing I care about with the model, because it's right, it's coming from conservation of mass and momentum. Then it's actually also solving current, so we know depth average velocities across the same place. So we use all of that, and then in the end, then I can get some estimate from the computer of storm surge at a particular place if I put in the hurricane, which is represented here by surface stress. So the model that I primarily use is called AdCirc, which is short for the Advanced Circulation Model. So my PhD advisor was a key developer in this model, as was Rick Ludick and Johannes Westerink at Notre Dame. So there's like a cohort of people that kind of developed this model. And what's special about it, there are other shallow water models, hydrodynamics models, but this one is kind of unique in that it doesn't require structured meshes. So, right, this means that in essence, things can change in spatial resolution. So in space, the numerical discretization method, so we have these equations, then we need to discretize them, put them on a computer, reduce it to a linear system of equations, and solve it. Okay, but what's special about here is that when we discretize in space, we don't have to do it evenly. So if I want more resolution, if I want to have less error due to the numerics along the coastline, so you're looking at Florida is what I'm outlining with the mouse, then I want more resolution here because I want more accuracy here. But if I have to increase resolution everywhere just to get the refinement here, then the model becomes very expensive. So by using the finite element method, then I don't have to have a structured mesh and I can just resolve the model where I want it, which in my applications are along the coastline. So it's a really good model for this. It's still quite expensive, which I'll kind of come back to in the end as I discuss where we're going forward. But it is a really good physics-based model. Okay, so what this allows us to do again is to kind of do scenario-based modeling. And so that's what we did in this 2020 paper, I want to say, where I worked with some atmospheric scientists at NCAR who had developed a data set of hurricanes as they existed and then also as they might exist, 2021 paper. So the WRF model is a regional forecast model. It's 3D, it's convection permitting, so you can model rainfall. It has high resolution for this type of model in the horizontal like plane. And then it also has 51 vertical layers, so good resolution in the vertical direction. And so this is used to model weather and can be used to model hurricanes. So what Ethan Gutman, my collaborator at NCAR, did in a 2018 paper was he applied a climate change signal on the boundary, which was representative of one of the emission scenarios from that time. And so basically, the emission scenarios, if we more or less downscale that information, we can see the effects on zonal and meridional wind speeds, sea level pressure, geopotential height, all of these things that really impact what a hurricane might do. And so then in this paper, he modeled hurricanes as they happened. So 20, I think it was 22, but we couldn't get one of them in our paper to run. But a number of hurricanes as they happened, and then again with the climate change signal. And so what they were able to do was kind of compare with this climate change signal on the boundary of their weather model, how did the hurricanes change? And so this paper discusses like what's the effect on that maximum wind speed and translation speed, the size of the storms, etc. So in 2021, I worked with a grad student and Ethan to understand what's the implication for surge by basically coupling their hurricane model to our storm surge model, AdCirc. And then in the end, we're able to see like what's the difference in the surges across the domain. So this is the domain that we use. It's called the HSOFS mesh because it's high resolution and it goes over land. So you can see like in the bottom of Florida, then it's green because the mesh actually extends onto land. And so that's not typical for an AdCirc mesh. Usually we'll kind of model what's going on up to the boundary, and then we'll do some post-processing method if we really have questions around what's going on over land. So it's a good mesh in that sense, but it doesn't have the resolution you would need for like a building. So the finest resolution over land is like 150 to 50 or 500 meters, right? Which is quite large for maybe the applications a civil engineer is used to. But there can be some like intermediate step where we have a good estimate of maybe what the representative bottom friction is there given what's there. If there's a city with lots of development, then we might use a bottom friction coefficient that simulates that and get a good idea of what the surge should be based on those physics. So it's a high resolution mesh. So it has 1.8 million vertices, which just means in this triangle discretization, that's how many vertices of the triangles we have. That's how many places we're solving for H, or the total level of water. Okay, so I think also of note here, we didn't account for sea level rise at all. So there's no uncertainties introduced by the uncertainties around sea level. We're just simply looking at what was the surge if we model the storm as it happened, and what was the surge if we model the storm as it would have happened with climate change conditions. And so this is an example of one of the results where we're modeling Hurricane Ike, which struck Galveston Bay, which is an island off Houston. So this is Houston, and then this is the Gulf of Mexico. And so qualitatively, you're kind of just seeing, okay, there's more red and it looks more intense further up, right? So even like in this inland area, there's green on this side, which is something like 3 meters, but over here, then that's red, right? So you're seeing that there's more surge with the end of century storm. And then we quantified some of the values there by calculating what's the inundation volume, so how much water is actually going onto land, and then also the areal extent. So, right, how many areas is this actually affecting? So we did this for 21 storms, as I mentioned, and so these are listed in decreasing order of the, let's see, decreasing order of either today's or the future, because they don't go, yeah, so here. So increasing order or decreasing order of the control scenario. So that's the hurricanes as they happened, right? So the storm that produced the most inundation was Ike, then Isidore, then Rita, and so on. And then when we add the climate change signal to the boundary of the hurricane model, then we measure inundation volume again. And so in the paper, we have like a similar table for area. So we can say some things about, right, what's producing more inundation as far as water on land, but also then aerial extent. So here, what we're looking at is the change from the control or the present day condition to the climate change condition. And so I guess you can see a couple of things. So one, everything's not positive, but kind of in the mean, they are positive. And most of the storms are like do have a positive change. So more storm surge by the end of the century conditions. Um, and then also we started to kind of look at things by characteristic. So here you should look along so these storms are just listed in order of the inundation volume. It's going from increasing or the smallest to the largest as far as like the change, right? So what had the largest change is Hurricane Francis. So 2004, Francis, the inundation volume increases by 161%, right? So there's the greatest increase. Okay, and then the least was Ivan, which didn't change at all, which we think was just no, so it actually decreased, sorry. So it decreased, and so that's for a variety of factors. So what we wanted to look at is if we then back out what was the change that was found in the 2018 paper. So did it correspond more or less to the changes we saw in wind speed, radius, translation speed, and pressure? And those are the characteristics that they studied in their paper. So a red color increases or defines like increased intensity. So for pressure, for example, a lower pressure is a more intense storm. So if there was kind of a negative change, that's the pressure getting lower or the storm getting stronger. So we would measure that as red. So in essence, you're looking for red to go with red and blue to go with blue, but we see that's not happening. So for example, like for Hurricane Isabel, each of these four storm characteristics is intensifying. So the wind speed is getting stronger, the radius is getting larger, the translation speed is getting slower, which is known to cause more surge on the open coast, and then the pressure is getting lower, right? So it's intensifying. But then the net result is actually less inundation volume. And then we see the opposite effect for Dennis, where all of the characteristics are decreasing in intensity, but then the volume is actually increasing. And so what we kind of are understanding is that it's not as simple of a relationship as we would think. So again, kind of reinforcing the message from the Saffir-Simpson work is that, just because you increase wind speed doesn't necessarily mean you'll see an increase in inundation volume. And so it kind of motivates the need for this type of physics-based modeling to really understand all of the impacts. Okay, then we also tried to do something similar by separating. So instead of looking at changes, just kind of looking for a direct correlation between um, the in like a characteristic and the volume. So here again, the storms are ordered from decreasing volume to increasing volume as opposed to the change on the other graph. And so what we would expect is to see kind of the same lighter to darker gradient in each of the characteristics. And right, we don't. We see kind of this checker box thing where there's not really a one-to-one correlation between how the properties change and how the inundation volume changes. So we have like a clear need for computational modeling and physics-based modeling that shows these processes. And again, that relates to, that's a point that came out in both of those papers. So here was kind of the overall result, like in one picture, where we're just looking at the differences across those 21 storms. So we're just measuring that change that I showed on the other plot, but on a map. So we can see this is kind of like a consolidated graph. So we're looking at all of the storms together. But if all of the same set of storms had happened in the future climate, then we would expect to have seen more surge in all of these places and then less surge in these few places here that are blue. Okay, so I showed this image before, and so kind of the idea here, which I may push through a little faster, but is that it's nice to look at scenario-based modeling and just kind of get an idea of like, oh, if the same under the exact same conditions, what could we expect? But maybe you know that that's not really how civil engineers think. So if we're building a structure or designing a building, then it has to be built with a more probabilistic assessment of risk in mind. So I mentioned here, like we're looking at the 100-year flood plain. And so that's the kind of number that we actually want. So I will go through that a little bit. So instead of just knowing, oh, Ike would look like this in the future, what I'm saying is like knowing that is useful for science, but it doesn't really help us design a building, right? We're not designing buildings to withstand Hurricane Ike. We're designing buildings to withstand particular levels of flooding or flooding levels that have particular probabilities. So we want probabilistic assessments like this. And so I guess rather quickly, like there's one methodology that we've used to do this. So this is the work that I started in my postdoc, where we're using extreme value analysis to really get that kind of probabilistic assessment. So in this case, we're looking at kind of the maximum storm surge of a number of hurricane storm surges. So a storm surge has like a time component, but really when we're designing, then we care about the max values and we don't care about all of them or the mode of them. We care about the tail end of the distribution. So our main interest is in the low frequency but high impact event. So if we think about like a 3-foot storm or 3-meter storm surge, that's not something that happens often, but we want to be prepared when it does because the impacts are great. And so for this, we can use extreme value analysis. And in particular, one of the methods that I've used is called the generalized Pareto distribution. And so basically you set a threshold where like this is the level that we care. So here I'm calling it H max. So it's like anything that's 2 meters or above is where I really want to get the analysis done. I'm not so worried about the 1-meter storm surge because presumably, our infrastructure is built in a way that can withstand that. So if we know the probability that we exceed this threshold, then we basically can fit this tail of the distribution and then use that to understand what is the return curve, which I usually explain, but maybe the engineers understand, but it's basically describing probability of like an extreme event. So if I have 100, if this is my return curve and I look at the 100-year flood level, it's telling me that the 3.5 meter is the 100 level event, which means it has a 1 over 100 or whatever that number is probability each year, right? So the 500-year flood is the level. So here 4.1 that has a 1 out of 500 chance of exceedance each year. Okay, and so those are the numbers that engineers like to build around. Okay, so by definition, when we're talking about extreme values, these are low frequency, so we generally don't have that kind of data. Um, so on top of it, if we want to know kind of the risk at a particular place, we definitely don't have that much local data because the hurricanes don't occur that often. And when they do, we don't have enough data historically. So it's hard to implement this method with existing data, as opposed to like if you're looking at river discharge, you have plenty of data because that we see that much more. So historical data alone is unreliable for understanding evolving flood risk due to climate change. So data alone is insufficient because you don't have enough. But then also, if we want to understand what's happening in future climates, then we don't, right? We can't use historical data for the same reasons I said before. So what we've done before is just use synthetic hurricanes that are representative of a future climate, right? And so they're generally dependent on the climate model that we use, but you can get like a distribution of maximum wind speeds or radius of maximum wind speeds. And basically that is used in simulation. And then we simulate all of the maximum storm surge and then do this distribution, construct this probability distribution. And then additionally, we know part of coastal flooding is also impacted by mean sea level rise, which is also uncertain, and better described by probability distributions. So mathematically, we can take a convolution of both the distribution we get from our simulated data and then also the distributions we get from projections of sea level rise, and we can integrate them so that we get a final probability distribution from which we can understand 100-year flood, 500-year flood, etc. And so this is kind of a graphic that's kind like trying to describe the framework, but basically you have some emission scenarios, so like RCP 8.5 or something else, which is going to cause local mean sea level rise, right? It's going to affect the local mean sea level rise, but it's also going to affect the hurricane. So we going to combine these both and integrate them into surge modeling. So you could do that a couple ways. You can convolve the probability distributions, or you can put it in directly to the hurricane model if you do more deterministic stuff. And then you can construct the return curves using the extreme value analysis and do coastal flood hazard assessment. So this is kind of the framework. And so we did this before for 4 locations. So Jamaica Bay at the top, but then also these other 3. And so these were just identified as kind of high risk areas that we wanted to understand more. So I just want to give you kind of an example. The point of this was not to go through the results in detail, but I'll point you to the paper where this is kind of so these are for Jamaica Bay. This is the return curve we get with that methodology where we see the 100-year flood is 3.3 meters. But then when we integrate or convolve the distribution with sea level rise, then we see that return period shift to 57. So the 100-year flood rises and we see it go from 3.3 to 3.7. But what's more important is, right, if you're a civil engineer and you're building for the 100-year flood level, you're building for 3.3. And then it turns out that's insufficient. It's almost twice as likely if you account for sea level rise. If you account for, more extreme values of sea level rise, which may be projected for later in the century, then it's an even worse underestimate. And then we use a modeling approach where we could simulate changes in hurricane storm climatology and kind of go through the same exercise. And so what we saw was basically your 100-year surge going to the 34-year surge or becoming 3 times as likely. And similarly, by the end of the century, it would go to the 6-year surge, right? So that's like more than 10 times, almost 20 times as likely. So, kind of the big takeaway here is that you need to account for sea level rise in design, but you also need to account for the changing storm climatology. So, this like NCEP line is telling you, oh, account for sea level rise if you want a structure to withstand something for over a century. But this is telling you, like, if you don't also account for how the storms change, then you're underestimating the probabilities that you'll see it each year. Okay, so all of these details are kind of spelled out in both a book and a paper, right? So that's just one example. And so I'm just using this to kind of illustrate that like probabilistic risk analysis is really informative and it's useful for civil engineering application because you get the probabilistic estimate of risk. But it's dependent on uncertain interdependent climate models, which is kind of another issue. And also you're limited by the computational costs of your models. So I showed you these kind of bar charts of all of these storm surges, which are reflective of like 2,000 simulations. And that's not something that's easy to do with this methodology, even though the outcome is more useful. So in the next stages of our research, so what we're doing now is we're trying to convert both the WRF model and the AdZerk model to more data-driven modeling approaches, which would make this whole framework faster, and so we'd be able to do it. So I'm again working with Ethan Gutman at NCAR and another atmospheric scientist, and so they are developing a WRF emulator, so the expensive computational model for the climate is going to be replaced by kind of a emulator that's based on Vision Transformer AI. And then I'm working with students in my group to develop machine learning methods or deep learning methods for AdZerk. So some of the models we've explored already are Bayesian optimization, tensor-based method, and then diffusion-based models, right? And so the whole goal is to kind of outline or combine the two approaches by making the computational costs more feasible. So just some concluding thoughts. So one, coastal communities are at an increasing risk of flooding, and we know this is due to sea level rise, but it's also due to changing hurricane characteristics. And so the ones that we've studied most directly are tropical cyclone intensity, size, translation speed. And then additional risk factors lie in civil engineering infrastructure. So I think there's plenty of opportunity for more data-driven modeling, right? So I mentioned like some of the issues with resolution, right? We may be able to explore more deeply if we use kind of data-driven methods. But also coastal population dynamics and demographic shifts. And multi-hazard. So these are kind of some of the applications that I look at and am interested in if you look at them and want to try to work together. And I think good examples of this are shown in these figures. So Hurricane Katrina, we saw a levee failure, right? So there's plenty of room for research in civil engineering infrastructure. Hurricane Sandy was so devastating because of the population density. So I've done some work before with students on kind of evolving population shifts so we can understand who's at risk based on projections of population. And then multi-hazards, for which I think Hurricane Harvey is a good example because there was such heavy rainfall with that storm that it kind of messed with the civil engineering infrastructure, the ability of water to drain, and caused a lot of flooding in Houston. So to conclude, I will say that computational mathematics and numerical storm surge modeling is an essential tool in non-stationary flood risk analysis. And the hope is that data-driven modeling, since it's everywhere now, can support more comprehensive methodologies. Okay, so that is it. And I would love to take any questions if you have them.